Good evening to all of you. Now, in this lecture, we are going to explore synthetic aperture radar remote sensing. So, synthetic aperture radar remote sensing basically works in the microwave region of the electromagnetic spectrum. So, we are going to first talk about microwave remote sensing. So, from the name, it is clear the remote sensing which is carried out in the microwave region of the electromagnetic spectrum is known as microwave remote sensing technique. The wavelength region from 1 millimeter to 100 centimeter of the electromagnetic spectrum is used for spaceborne microwave remote sensing technique. Not only spaceborne, airborne as well as the ground-based micro remote sensing technique also. So when we are talking about the microwave region or the propagation of electromagnetic wave, so definitely there will be one electric field vector, one magnetic field vector, both will be perpendicular to each other and mutually perpendicular to the direction of propagation of the electromagnetic wave. So here we can see that the electric field vector is represented by E, magnetic field vector is represented by M. The vibration of the electric field vector is represented in red color and the vibration of magnetic field is represented in the black color. So here you can see that both are perpendicular to each other and they both are mutually perpendicular to the direction of propagation of electromagnetic wave. That direction is represented here by C. So C is representing the direction in which electromagnetic wave will be moving or transmitted by the sensor. Now this is a very famous relation, and in remote sensing it might be possible that this has already been seen. It might be possible that you have already seen this slide in basics of remote sensing also. So here we can see that the relationship between the wavelength and frequency. The wavelength is the length of one wave cycle, which can be measured as the distance between the successive wave crests, and it is generally represented by the Greek letter lambda. And the frequency is represented by nu. So here you can see that the relation between wavelength and frequency is when wavelength will be multiplied by with the frequency, it will be equal to the speed of the light. So here you can see that c, which is the speed of light, will be equals to the lambda, which is the wavelength multiplied by the nu. So from this relation we can see that both are inversely proportional to each other. Means wavelength and frequency both are inversely proportional to each other. When there will be increase in the wavelength, there will be decrease in the frequency, and when there will be increase in the frequency, there will be decrease in the wavelength. This is the microwave band, the portion of the electromagnetic spectrum which is used in the microwave remote sensing. So here you can see that there are several the microwave band is divided in several subcategories, and these categories are Ka band, that is 0.75 to 1.1 centimeter, K band, that is 1.1 to 1.67 centimeter, Ku band, that is 1.67 to 2.4 centimeter. Then we are coming to the X band, that is 2.4 to 3.75 centimeter. Then the C band, which is covered in the wavelength region 3.75 to 7.5 centimeter. Then S band, that is having the wavelength range of 7.5 to 15 centimeter. Then L band, that is covering 15 centimeter to 30 centimeter wavelength range. And finally P band, that is having the wavelength range of 30 to 100 centimeter. So here what we are going to see that when we are moving from K band to P band, there is increase in the wavelength range and there is decrease in the frequency. Now here we will have to keep in mind that when the synthetic aperture radar sensors or the microwave sensors are designed, so usually they are designed in a single frequency range. Like if a sensor is designed for X band, so it is going to provide you the data set in X band only. It cannot provide the data set in C band or K band. The sensor which is designed for X band, it is going to provide you the data set in X band only. If one wants to use the multiple frequency ranges of the data set for their project work or for their research work or for their requirement, like they require the data set of P band, L band and S band, suppose 3 to 4 frequency ranges. At that time it is suggested to use the data set of different satellites which are, or different satellites and sensors which are working in these wavelength ranges. So here you can see that the different wavelength ranges are given here, and for different wavelength ranges, when we are talking about synthetic aperture radar remote sensing, so different SAR satellites have been designed and they are working in the different wavelength ranges, or you can say the different frequency ranges. Now when we are talking about microwave sensors, so generally most of the people are thinking about the active microwave only, but microwave sensors are also categorized in two categories: active microwave and passive microwave sensor. A passive microwave sensor detects the naturally emitted microwave energy within its field of view. This emitted energy is related to the temperature and the moisture properties of the emitting object or surface. Passive microwave sensors are typically radiometers. There are different applications of the passive microwave remote sensing that includes meteorological application, hydrological application, as well as the oceanographic application. The microwave energy recorded by a passive sensor can be emitted by the atmosphere, reflected from the surface, emitted from the surface, or transmitted from the subsurface. Now when we are coming to the active microwave remote sensing, so active microwave sensors are divided in two categories: imaging and non-imaging. Like from the name it is clear that passive sensors are those sensors which are not able to generate their own electromagnetic waves. They are dependent on any other source of energy to do the imaging or to get the information, to get the required information. But the active sensors, they are not depending on any other source of illumination. They will have their own source and they can generate their own electromagnetic waves, and those electromagnetic waves could be used to do the imaging or the information extraction. So active microwave sensors provide their own source of micro radiation to illuminate the target, and they are categorized into category imaging and non-imaging. The most common form of imaging active microwave sensor is radar. Radar is an acronym for radio detection and ranging. The radar sensor transmits a microwave signal towards the target and detects the back scattered portion of the signal, because when the radar sensor will transmit the electromagnetic wave towards the targeted object, so scattering will take place, and the amount of the signal which will be received by the sensor will be the back scattered energy. So the radar sensors, they are basically working on the back scattered portion of the energy. Here if you will see that generally the three different ranges of the electromagnetic spectrum are used in the imaging. Like in optical multispectral, we are using the visible and the reflected infrared portion in the imaging, and in thermal remote sensing we are using the thermal infrared region of the electromagnetic spectrum, and in micro remote sensing we are using micro region of the electromagnetic spectrum. So the different region of the electromagnetic spectrum, they will have the different properties. Like the optical multispectral, they are working based on the concept of the reflection of the electromagnetic wave. So there we are mainly talking about the reflectance. So there we are going to use the portion of the light which will be reflected by the earth surface or the object, that will be used in the imaging. Now in the thermal infrared, we are not using the reflected portion of the electromagnetic wave. We are mainly using the emitted portion of the electromagnetic wave. So that thermal emission will be mainly from the land use and land cover, as well as the other objects like sea surface also. So that thermal emission will be detected by the thermal sensors, and finally imaging will be done, and it will be possible to get the thermal properties of the targeted object. Now when we are coming to the micro remote sensing, so in microwave, particularly when we are talking about the active microwave, so there radar sensors are used to transmit the electromagnetic pulses. So here we are using the concept of scattering, and mainly the back scattered signal for the imaging purpose. So here you can see that in the three different remote sensing techniques, we are using three different properties of the electromagnetic wave. Now, when we are coming to the non-imaging microwave sensors, so non-imaging microwave sensors include altimeters and scatterometers. In most cases, these are the profiling devices which take measurements in one linear dimension as opposed to the two-dimensional representation of the imaging sensors. But it is also possible to do the imaging with the help of the scatterometers. But in most of the cases, they are the profiling devices. Now, radar altimetry, when we are talking, so radar altimetry is used on aircraft or spacecraft for altitude determination and also for the topographic mapping and the sea surface height estimation. Scatterometers are also generally non-imaging sensors and are used to make the precise quantitative measurements of the amount of energy backscattered from the targets. Scatterometers and altimeters both have the different other applications. Now, our lecture is mainly focused on the synthetic aperture radar remote sensing. So, synthetic aperture radar is a form of radar that is used to create images of objects such as landscape. These images can be either two or three dimensional representation of the objects. Now, as we are knowing that the remote sensing which is carried out in the microwave region of the electromagnetic spectrum is known as microwave remote sensing. Similarly, when one is talking about SAR remote sensing, so SAR remote sensing is an imaging active microwave remote sensing technique which provides higher spatial resolution data set. So here in this slide you are going to see the synthetic aperture radar image, a comparison between synthetic aperture radar image and the optical multispectral image. So here you can see that the image which is represented in different colors. So this is the true color composite image for the San Francisco area. So in this one can see that the objects are represented in their actual color or the true color information, but the image at the top, when you will see that this image, so this image is the image which is acquired by the synthetic aperture radar sensor. So this image is not having any color information. It means that it is clear that the microwaves are not sensitive to the color information of the targeted objects. So what they are doing? Actually, they are mainly sensitive to the structural and the electrical properties of the targeted objects. So that based on the structural and electrical properties of the targeted objects, they are having their backscatter nature or scattering properties, and based on the different scattering properties, that is depending on the structural as well as electrical properties of the targeted objects, we are going to get the backscatter signal, and the location where we are going to get high backscatter, that will appear bright, and the location where we are going to get the less backscatter, when there will be less backscatter. So it might be possible if the surface is smooth, so there will be specular reflection, so that time less backscatter will be received by the sensor. So those surfaces which are contributing very less in backscattering, so those are going to appear as dark, like water body, and the smooth surfaces, those are going to appear as dark, and the objects which are going to contribute in high backscattering, like urban area, urban buildings, so they are going to appear as very bright. So here you can see that very bright objects, these are visible. So these are high scattering which are received from the urban targets, and from the vegetation surface, from the vegetation cover, we are going to get the moderate scattering. It means that the water body and the smooth ground, plain ground, that are going to contribute in specular reflection. So those are going to appear as dark surface because they are contributing less in the scattering, and objects which are going to contribute high backscatter, like urban area, they are going to appear as bright. Now here we are going to talk about the radar geometry. So here you can see that the flight direction, this is the azimuth direction. Basically this diagram is taken from the remote sensing book of Dr. J.R. Jensen. So here you can see that the forward direction, or the direction in which aircraft or spacecraft is moving, that direction is known as the azimuth direction. It means that forward direction is the azimuth direction. And the direction in which SAR sensor is transmitting the electromagnetic pulses, that will be range direction. So here you can see that this range direction or look direction is either left side or right side, because SAR sensors are not nadir looking radar sensors. They are side looking radar sensors. SAR sensors are not going to transmit the electromagnetic pulses vertically, they are going to transmit the electromagnetic pulses in the side looking direction. That side looking direction will be either left side of the azimuth direction, or it may be the right side of the azimuth direction. By maintaining some angle, electromagnetic waves will be transmitted by the sensor, because ranging is important, so that there will be possible to generate the 2D images. Now here we are going to see the several parameters which are mentioned here. Like, as we are knowing, you have already seen the range direction as well as the azimuth direction. Similarly, there will be one very important parameter, that is the angle of incidence, or the incidence angle. So incidence angle is the angle between the incident electromagnetic wave, like here you can see that incident electromagnetic wave, and a normal drawn to the point of incidence. So the angle between the incident electromagnetic wave and a normal drawn to the point of incidence will be the angle of incidence. This angle of incidence is highly affecting the back scatter, because if the terrain is flat, then it is okay. But when the terrain is undulating, so the angle of incidence, the local angle of incidence, that will be influenced by the terrain's topography, is going to change the back scatter signal. Now here what we are going to see that when the electromagnetic waves, by maintaining some angle, they are transmitted by the SAR sensor, so they are illuminating a patch on the earth surface, and this patch is represented here. Now the illuminated area, or the swath of the SAR data set, will be in between the illuminated area, and the ranges are near range and the far range. So that according to definition, if you will see, one can easily understand that the portion of the illuminated area which is appearing near to the nadir will be known as the near range, and the farthest point from the nadir will be the far range. So the imaging swath will be in between near range to far range. Now when one will have the angle of incidence, so one can also calculate the depression angle, like here it is given depression angle. So depression angle is 90 degree minus angle of incidence. So 90 degree minus angle of incidence is going to give the depression angle. Now in this slide we are going to see a comparison between different sensors. So mainly we have selected here three sensors: LIDAR, optical multispectral, and SAR. So if you will see the platform, so LIDAR remote sensing is possible with airborne and spaceborne from both the platforms. Optical multispectral is possible from airborne and spaceborne both, and SAR is also possible from airborne and spaceborne, as well as the ground-based systems also. Now when we are coming to the radiation, since LIDAR and SAR both are the examples of the active remote sensing techniques, so they will have their own radiation. And when we are talking about the optical multispectral, so optical multispectral are the examples of the passive sensors, because they are dependent on the sun's illumination or the reflected sunlight. When we are coming to the spectrum, so LIDAR is generally operated in the infrared region of the electromagnetic spectrum. Optical multispectral is operated in the visual and infrared both. SAR is operated in the microwave region of the electromagnetic spectrum. Now when we are coming to the frequency, so LIDAR sensors are highly monochromatic, so they are working in a single frequency. Now from the name it is clear that optical multispectral means multiple spectra is there. When multiple spectra we are talking, it means that is multi-frequency. So the optical multispectral sensors will have the multi-frequency data set. And when we are coming to the SAR, so if you will have only one SAR sensor, like in C band or any sensor in X band, So one SAR sensor can provide the data set in one frequency range only. But if we are using the different satellites of the different frequency ranges, so at that time we can have the multi-frequency data sets also from the different SAR sensors, because like multi-frequency data set could be acquired like X-band data set from one sensor, C-band data set from another sensor, L-band data set from another sensor for the same area. So that data set may become the multi-frequency SAR data set. Now, when we are coming to the very useful information or advanced technology which are used to retrieve the useful information from SAR, these are the polarimetry and interferometry. So currently polarimetry and interferometry, these are currently not possible in space-bound remote sensing or airborne remote sensing with LIDAR and the optical multispectral. Why? Because due to the short wavelength ranges which are used in the remote sensing in the visible and near infrared or reflected infrared, because they may be easily they could be easily influenced by the atmospheric dust particles. So currently polarimetry, so at that time we cannot retrieve the polarimetric phase as well as the interferometric phase from the LIDAR and the optical multispectral sensors. But due to the long wavelength ranges, the microwaves are not generally influenced or affected by the atmospheric particles. So polarimetric phase and interferometric phase both could be easily preserved, and the polarimetry and interferometry could be easily done with the help of the synthetic aperture radar remote sensing. Okay. Now when we are coming to the acquisition time, so LIDAR and SAR both are the active remote sensing techniques. So they could be operated. They could these sensors could be operated in day and night both the times, because they are not affected by sun's illumination. So day and night both the time imaging will be with the same concept. There will not be any difference. But optical multispectral sensors, to get the information of the Earth surface, fruitful information of the Earth surface, they are mainly operated in the daytime. Now when we are coming to the weather, so LIDAR and optical multispectral both could not be operated in the cloudy situation, because these electromagnetic waves which are used in the visible and the infrared ranges, both the ranges are having very small wavelength ranges. So both could be easily blocked by the cloud cover. So these could not provide any information when the atmosphere will be cloudy. But when we are talking about synthetic aperture radar remote sensing, so since the electromagnetic waves or the microwaves are having very long wavelength ranges, and they can easily penetrate, they can easily pass through the cloud cover, and they can interact with the earth object, and they can provide the earth objects information even in the cloudy situation. Now this is the list of some earth observation SAR satellites. So RISAT-1, it is written here. This was launched in 2012, and this worked till 2017. This was launched by ISRO India, and this satellite was launched mainly in the hybrid polarimetry in C-band. RISAT-1A or EOS-04, that was recently launched, that was launched last year on 14th February 2022. This is a very advanced satellite, and this can provide the data set in hybrid polarimetry as well as the quad pole mode. Because if you will see all the satellites, currently working satellites, they can provide the data set either in dual pole mode or the quad pole mode. But RISAT-1A is the satellite which can provide the circular polarimetry based hybrid polarimetric data set as well as the fully polarimetric quad pole data set also. Now when we are coming to the RadarSat series of the satellites, so RadarSat-1, RadarSat-2 and the RadarSat Constellation mission, these are the satellites from the Canadian Space Agency. So these satellites are also launched in the C-band. Now when we are coming to the satellites of the European Space Agency, so ERS-1, ERS-2, Invisat, Sentinel-1A and Sentinel-1B. These are the satellites of European Space Agency, which are launched in the different years. So here we can see that most of the satellites which we are there which we have seen, these are in C-band. Now when we are coming to the L-band satellites, so JERS, this was launched by JAXA, Japanese Space Agency. That is that was in L-band, that was launched in 1992 and it worked till 1998. Then in continuation to the L-band satellite, JAXA launched ALOS Pulsar in 2006. It was able to provide the quad pole data set. Then when it stopped working, ALOS Pulsar, then in 2014 another satellite ALOS-2 Pulsar 2 was launched, and this is also very advanced satellite, and this is providing the quad pole data set as well as single and dual polarized, but this is also able to provide the quad pole data set. Now when we are coming to the X-band SAR sensors, so TerraSAR-X and TandemX, these are the satellites from the German Space Agency. These satellites were launched and these are providing the data set in quad pole. These satellites are still working. Now we have seen that few famous satellites. A detailed list is also there, and we are going to see the comparison of the various SAR bands. So currently we do not have any P-band SAR satellites. European Space Agency has proposed to launch, and I think in this year only they will be launching the satellite Biomass, and this satellite will have the P-band will have the high penetration capability, and it can penetrate the canopy cover. It will have the subsurface penetration capability. It can provide the information of the buried objects. It could be used for the archaeological application, and the wavelength will be approximately near to 70 centimeter. Now when we are coming to L-band, so in L-band we have the several satellites. CSAT, which was the first satellite launched in SAR remote sensing. That satellite was mainly launched by NASA JPL, and this satellite worked in L-band. So CSAT, JERS-1, ALOS Pulsar, ALOS-2 Pulsar 2, SAOCOM, NISR L-band, TandemL. These are the satellites which covers the past satellite, present satellite and the future satellites also. All these satellites are in L-band. The L-band will have the good penetration and it could be used for the forestry and environmental monitoring applications. Now when we are coming to the S-band, so S-band will have approximately 10 centimeter wavelength. So Almaz 1, SG1C, Condor E, NOVA-SAR, NISR S-band. So these are the satellites in S-band. So this could be used for the ship detection, ice mapping, oil spill detection. Oil spill detection could be done with any range of the SAR sensor, like it could be done with the X-band also, C-band also, S and L-band. Now when we are coming to C-band, so again there are several satellites, ERS-1 and 2, Invisat SR, RadarSat 1, 2, RCM Constellation Mission, RISat 1 and 1A, and then Sentinel-1A and B. So these have been widely used for the agricultural application, for the ocean feature detection, for glaciological application. So these satellites have been widely used for the different applications. Now when we are coming to the X-band, so approximately 3 centimeter wavelength range is used. So TerraSAR-X and TandemX, Cosmo SkyMed, TechSAR, RISat-2, PAJ, ComSat-5, ICI Constellation. These are the satellites which are working in the X-band, and they are very much sensitive to the surface roughness, and these are also used to create the high resolution images for the different applications and topographic mapping as well as the flood mapping and monitoring. Now this slide shows the Indian SAR Earth observation satellites. So RISat-2, this was launched in April 20, 2009. This satellite worked in X-band. RISat-1, this was launched on 26th April 2012. This satellite worked with C-band in hybrid and dual pole mode. RISAT 2B and 2B-R1 as well as 2B-R2. These were the satellites which were launched in X-band. These satellites were launched in 2019 and 20. Now RISAT-1A EOS-04, that is renamed as EOS-04, that is recently launched last year, February 14, 2022. And this is very advanced satellite which is having the capability to provide the data set in quad pole mode as well as the hybrid polarimetric mode. Now NISR mode, this is also like most technical and most advanced satellite, because this is the first satellite in the Earth observation which will be launched with dual frequency, because in the previous slide when we were comparing the different bands and different satellites, so there we have seen that NISR was written with L and S both. So NISR will have the capacity to provide the data set in two frequency ranges, L band and S band. But I want to say that before NISR is the first satellite for the Earth observation, but ISRO India has already launched the dual frequency SAR sensor. That sensor is DFSAR with Chandrayaan 2. In Chandrayaan 2 mission, we already had launched the dual frequency synthetic aperture radar sensor DFSAR, which is still working. It is providing the data set, high resolution data set of the lunar surface, even for the dark polar regions. So those data sets are available, one can download, and if they are interested, they can also work. So for first satellite in dual frequency, that is already launched by the ISRO India, but NISR will be the first satellite in Earth observation which can provide the dual frequency SAR data set. Now, one should understand the need of the SAR dataset when we want to work with the SAR dataset. So we should understand the need of the SAR dataset. So this is a slide in which we are going to compare the optical multispectral dataset and RISAT-1 hybrid pole dataset, and both are the false color composite representation, because here in list 4 like infrared band is are represented by red color, and the red band is represented by green color, and green band is represented by blue color, so that the standard false color composite image has been generated here for the Doon Valley forest ranges, in which Barcode forest range we can also see, Barcode forest range, and Rishikesh forest ranges, and the Rishikesh city, the holy river Ganga. So, and the dry river channels are also there, we are able to see. And this is because we are knowing that the SAR sensors are not sensitive to the color information. So with the help of the different polarizations, this false color composite image has been generated. Now when we will do the image interpretation, both the images are of different seasons, or we can say that of different time periods, but features are approximately similar, only we are going to get the high amount of water body. So from the first look, it might be possible that optical multispectral data set will be appearing good for the visualization. Anyhow, no one can replace the optical multispectral data set, because our eyes are working in the visible range of the electromagnetic spectrum, and out of the 4 band which are used here in the imaging of the optical multispectral, 3 bands are of the visible band only, and in this representation, out of 3 bands, 2 bands are of the visible range. So anyhow, the visible data set, or the data set which were acquired in visible range, they are going to appear better for the visual image interpretation. But SAR data sets are not only for the visual image interpretation, they are mainly used for the information extraction. So what kind of information we are going to extract, that we are going to discuss. Now I have taken the zoomed portion from the one band of the list 4 data set and one polarization of the RISAT-1 data. Now just see the Pashu Log barrage, which is encircled here in the red color. So in the optical multispectral data set, we are, from our image interpretation skill, we can say that there is some object which is blocking the water body, but the object which is blocking the water is not visible, and we know that those objects will be generally the construction of the barrages. Barrage is there, but the color of the barrage is merged with the background water, and we know that optical multispectral is mainly sensitive to the color information. So even in the false color composite image also, if you will zoom it, you are not going to see those barrages. And here in this band also, this is not visible. But if you will see the same area in the SAR data set, so here you can see that SAR data sets are not sensitive to the color information. They are mainly sensitive to the structural and electrical properties of the targeted object. So mainly when we will talking about the structural property, so structural and electrical, both the properties of the barrage will be entirely different than the background water. So that the barrage is contributing in the high back scatter, so that this is appearing as bright patch. So one can easily detect this target. Other features are also visible, like here the terrain information is not clearly enhanced, that we will see in the next slide. So in the next slide, when you will see that there is another barrage, this is Bhimgowda barrage near to Haridwar. So again this barrage is not visible because the color information, color of the barrage is merged with the background water, so that this is not visible. But the same barrage is clearly visible in the optical multispectral data set, in the SAR data set. Now when we are comparing the terrain's topography, so here terrain is undulating. Just focus on these river channels and the undulation of the terrain. You can see that in the optical multispectral data set, some information of the terrain's topography is there, but that information is not sufficient and it is very less. But you can see that SAR data set, the clear undulation of the terrain could be easily seen. The clear information or the undulating terrain information could be easily extracted or easily visualized in the SAR data set, and that is not clearly visible in the optical multispectral data set. Similarly, other area here also you can see that the undulation is clearly visible in the SAR data set, and those are not clearly visible in the optical multispectral data set. So generally for the 3D information retrieval or for the digital elevation model generation, it is always preferred to use the SAR data set to get more accurate topographic information from the digital elevation models. Now this slide shows the penetration capability, the soil penetration capability of the SAR data set. So this is the Sahara Desert area. So just focus on the middle strip. If you will see that middle strip, so we are able to see that in the optical multispectral data set, the golden yellow color could be easily seen here for the Sahara Desert, because the optical multispectral data set is sensitive to the top color information of the object. So top color is mainly the sand. Now when the same area was imaged, the middle strip was imaged with the help of the SAR-A, shuttle imaging radar A, that was L-band sensor. So here you can see that L-band is able to penetrate the surface and it is able to interact with the subsurface, and here you can see that we are able to get some other structural information. These are basically the subsurface features, and these are the paleo channels which could be easily seen. Now when paleo channels are there, so one can easily understand that there was water body in the past. It means that the Sahara desert, which that is desert today, that was not a desert in the past. Several thousand years before, this area was green, because the paleo channels are showing that in the past, several thousand years ago, the water body was there. Now this slide shows the cloud penetration capability of the SAR data set. So here you can see that this is the data set, Sentinel-2B data set, multispectral instrument data set of the Sentinel-2B. At that time this data set, there was no cloud cover on the 24th February 2021. So at that time we are able to see that this is the image near to Varanasi. The Varanasi city is here, and for all the agriculture belts you can see that the agricultural crops are clearly seen in the red color and the pink color in this area. Now when the image was acquired on 15th January 2021, at that time there was cloud cover and we were not able to extract any information of the targeted object. But if you will see the Sentinel-1A data set of the same date, that was on the 15th January 2021, in VV and the VH polarization. So we can easily see that SAR dataset can easily penetrate the cloud cover. It can provide the information of the targeted objects. Now when we are coming to the SAR imaging, so here you can see that SAR is an example of the active remote sensing technique. So it transmits the electromagnetic pulses, and it receives the back scattered information, and imaging is done. Now the water body is appearing dark, cities are appearing as a bright passage, and all the other objects, they are appearing in according to their back scatter properties. Now SAR geometry we have already seen. So this is the graphical representation of the optical multispectral data set, as well as this is the SAR data set, appearance of SAR data set. So we are not going to go in very much detail of this. Now due to the two different directions, like azimuth direction as well as the range directions, there are two different resolutions of the SAR data set. So SAR data, in the case of SAR data sets, there will be two different resolutions within single SAR resolution cell, and those resolutions are azimuth resolution and range resolution. Azimuth resolution describes the ability of an imaging radar to separate the two closely spaced scatterers or targets or objects in the direction parallel to the motion vector of the sensor. Or you can say that this is the azimuth resolution describes the ability of the radar sensor to distinguish two closely spaced target in the azimuth direction. And range resolution, for the radar to be able to distinguish two closely spaced elements, their echoes must necessarily be received at the different times. So this gives the capability to create the range resolution. So range resolution is the capability of the sensor to detect two closely spaced objects in the range direction. Now here we can see that the azimuth resolution and the resolution. So azimuth resolution is depending on the antenna size. Larger the antenna size, higher will be the azimuth resolution. And range resolution is depending on the pulse width. So here you can see that actual antenna size is very small, and with the help of the concept of synthetic aperture radar, because the name synthetic is given, that synthetic means virtual. So what is happening, the total distance traveled by the SAR sensor to capture a point target, like this, suppose this is the first point, when the point target will be detected, or scattering from this point target will be received by the sensor. So sensor will be transmitting and receiving the information from different location, from this point, from this point, from this point. Suppose this is the middle point, that is the nearest point to the point target object. After that, again it is transmitting and receiving, transmitting and receiving. Suppose this is the last point, beyond this point, SAR sensor will not be able to capture any information of this targeted object. So what will happen, from first point to last point, SAR sensor will have the back scattered signal information for this point target. Now when all the echoes or the back scattered signals which are received for this point target from first point to the last point, when this will be merged, so what will happen, the entire distance traveled by the SAR sensor to capture the echoes of this point target or the back scatter signal of this point target will behave like a very large virtual antenna. Actual antenna is of a small size, but when we merge all the received signal, so the total distance traveled by the SAR sensor will behave like very large antenna. So the name is given synthetic aperture. So synthetic aperture length is very much important to generate the higher azimuth resolution. So the name is given synthetic aperture radar, so that very high spatial resolution images could be generated for these regions. Now in this formula, R0 is representing the range distance, the distance from the sensor to the target, that will be of several hundred kilometers, and lambda will be the wavelength which is used in the imaging, and a small LA will be the small LA with the actual antenna length, capital LA will be the synthetic aperture length. And so here we can see that the antenna, the azimuth resolution is directly depending on the antenna length. Now when we are coming to the range resolution, that is C tau divided by 2. Now here you can see that when suppose tau is 1 microsecond. So 1 microsecond, when you will convert 1 microsecond in the distance by multiplying it with speed of light, this will come to the 300 meter. Now it means that the resolution will be C tau divided by 2. It means that the range resolution will be 150 meter. Now here you can see that distance between the two aircrafts, the distance is 100 meter only. It means that this is smaller than the range resolution. At that time, what will happen, when the electromagnetic pulse will be returned by the SAR sensor after interaction, so the sensor will not be able to receive the two different pulses, because they do not have the sufficient distance to give the two separate pulses. So the sensor is going to detect both the objects as a single large object, because here you can see that in the return signal a large echo is received. Now in the case of when the distance is 200 meter, this is larger than the range resolution 150 meter. So here you can see that there are two separate back scattered signal or two separate echo from this targeted object. So both the objects will be placed in two different resolution cells, and both will be identified as two different objects. Now we are coming to the slant range and ground range. Like here this is the graphical representation of the SAR data set. Like here A, B, C, D, these are representing the ground range object information, or the true object position in the on the earth surface, and A dash, B dash are representing their visualization in the SAR data set. So what we are going to see, A is coming in the near range, and here you can see that I is coming in the far range. H and I are coming in the far range. So what we are going to see, the objects appearing in the near range, because SAR sensors are side looking radar system. So due to the side looking property, the objects appearing in the near range, they will be compressed in their shape and size. Here you can see that objects appearing in near range, they are compressed in their shape and size, and objects in the far range, the compression is less. So when we will have the SAR data set, so our first task should be to get the clear visualization of the objects. Our first task should be slant to ground range conversion to minimize the slant range ambiguity. Now when we are coming to the radar remote sensing or synthetic aperture radar remote sensing, so there we are using the polarized electromagnetic wave. Why? Because unpolarized energy vibrates in all the possible direction perpendicular to the direction of the propagation of the electromagnetic wave. At that time, what will happen? The electric field vector will be free to move in any direction in between 0 to 360 degree. So at that time, what will happen? In the received signal also, the signal will be moving from 0 to 360 degree. So the polarization of the signal will be moving from 0 to 360 degree. So at that time, the imaging will become very difficult. The clear imaging of the object will become very difficult. So that the polarized electromagnetic waves are used here. Polarization of electric field vector will be mainly taken. So electric field vector will be vibrating either in the horizontal direction according to the propagation axis, or it will vibrate in vertical direction according to the propagation axis. So based on that, there are mainly 4 polarimetric combinations which are generated. These combinations are HH, HV, VH and VV. So HH combination, we can see that horizontally polarized electromagnetic waves were transmitted, and after back scatter, horizontally polarized electromagnetic waves were received. So that this combination becomes HH. HV, when the horizontally polarized electromagnetic waves are transmitted, and at the time of receiving, vertically polarized electromagnetic waves were received. So this combination become HV. Now in the case of VH, vertically was transmitted and horizontally was received. In the case of VV, vertically polarized was transmitted and vertically polarized was received. Now here we can see that there are maximum 4 polarimetric combinations. If a SAR sensor can provide the data set at least a single polarization, suppose any one polarimetric combination it is able to provide out of the 4 polarimetric combination, then that data set is known as the single polarized SAR data set. If the SAR data set can provide the 2 polarimetric combinations out of these polarimetric combinations, then that data set will be known as the dual polarimetric SAR data set. If a SAR sensor can provide all the 4 polarimetric channels at the same time for the same area, then that data set will be known as fully polarimetric quad pole data set. So here it is showing the SAR imaging. SAR sensor will transmit the horizontal or vertical polarization. So suppose this is transmitting the horizontal polarization. So after scattering, it might be possible that polarization will be broken, since the transmitted signal was in horizontal polarization. So at the time of back scattering, most of the vibration of electric field vector will be there in the horizontal polarization only, but some portion will start vibrating in the vertical direction also. So here horizontal polarization is represented in black color, and the vertical polarization is represented in the red color. So here you can see that from single transmission of the horizontal polarization, we can receive two different polarizations of the channels like horizontal and vertical. So from single transmission of the horizontal polarization, we can generate the two different polarimetric combinations, that are those combinations are HH and HV, means horizontally transmitted and horizontally received, and from the same horizontally transmitted, vertically received. Now the same will be there with the vertical polarization. Vertical polarization will be transmitted, and vertical and horizontal both will be received, so that the combinations VV and VH will be generated. Now the SAR data consists of high resolution reflected returns of the radar frequency energy from terrain that has been illuminated by a directed beam of pulses generated by the sensor. The radar returns from the terrain are mainly determined by the physical characteristics of the surface, such as surface roughness, geometric structure, and orientation. The electric characteristics, dielectric constant, moisture content, and conductivity, and the radar frequency of the sensor. So these properties are going to affect the backscatter nature of the data set. Now here we are going to see about the surface roughness. So there is relation between the wavelength lambda, depression angle gamma, and the local height of the object h. So the surface roughness criteria is depending on the wavelength, depression angle, and the local height of the object of the surface. And this criteria was given by Rayleigh. So this is the Rayleigh criteria: a smooth surface criteria, smooth and rough surface criteria. When the object height will be less than or equal to the lambda divided by 8 sin gamma, where lambda is the wavelength, gamma is the depression angle, and h is the object height on the surface. So at that time, that surface will be known as the smooth surface. And if the object height will be greater than lambda divided by 8 sin gamma, then that surface will be known as rough surface. Now there was another criteria, modified Rayleigh criteria, that was modified by Peake and Oliver. This was working very well in all the condition. So according to Peake and Oliver modified Rayleigh criteria, the smooth surface criteria will be any surface will be smooth if object height will be less than lambda divided by 25 sin gamma, and a terrain will be known as bright, or a terrain will be not bright, sorry, a terrain will be known as rough, a surface will be known as rough if the object height object height h will be greater than lambda divided by 4.4 sin gamma. Now if the object height of the terrain is coming in between these two, then that will be known as the intermediate terrain. Now I would like to show, like you can put this criteria and you can calculate the rough, smooth, and intermediate surface criteria for different target. But I would like to show one point, like the object which is appearing as the object height which is appearing as a rough surface for aircraft Ka band, that is appearing as a smooth surface for CSAT L band. Like here you can see that according to the smooth surface criteria, surface roughness criteria, for aircraft Ka band with lambda equal to 0.86 and gamma equal to 45 degree, all the surfaces which will be having object height greater than 0.276 centimeter, they will be appearing as a rough surface. But the same surface, if you will see that for CSAT L band with lambda equal to 23.5 centimeter and gamma equal to 70 degree, this surface is going to appear as suppose object height is 0.5 centimeter. At that time 0.5 centimeter is going to appear as rough surface for Ka band, but that 0.5 centimeter object height surface will appear as a smooth surface for CSAT L band. Now radar backscatter is function of angle of incidence also. When in the near range there will be very high return that will be received by the sensor. So in the near range where high scattering will be received, in the far range less scattering will be received. Now the radar return is also depending on the undulation of the terrain. So here you can see that slope of the terrain. So here you can see that when the radar sensor is transmitting electromagnetic pulses, So what will happen here, so when the local angle of incidence will be calculated with the help of this slope. So what will happen, the angle of incidence will be very less, and at that time these surfaces are going to appear bright, so that these surfaces appearing bright, and the location where angle of incidence, local angle of incidence will be very large, so those surfaces are going to appear as dark. Now here we are going to talk about the interaction of electromagnetic wave with soil. So dry soil is, in the case of dry soil, what will happen? The electromagnetic wave, incident electromagnetic wave will penetrate the soil, so less scattering will be there, high penetration will be there, high penetration and less scattering, so at that time less back scatter will be received by the sensor. Now in the case of wet soil, due to increase in the dielectric properties, there will be less penetration, but when there is less penetration there will be high scattering, so high back scatter signal will be received by the sensor. Now when we will have the SAR data set of the two agriculture fields, one is having the dry soil, another is having wet soil. So in the SAR data set, wet soil agriculture plot is going to appear as a bright object, and dry soil agriculture plot will be appearing as dark object. Now when the soil will be flooded, so surface will be perfectly smooth, so whatever the information that will be transmitted by the sensor, entire information will be reflected away from the direction of the sensor. So at that time flooded soil is going to appear a dark feature in the SAR imagery. Now there is volume scattering, there are different scattering also. So one very famous scattering, that is volume scattering, that is mainly contributed due to the multiple scattering, and mainly these are contributed by the vegetation as well as the vegetation, or you can say that cornfield or the paddy crop, or as well as from the forest area also. Now here you can see that in X band, C band and L band, their response in the pine forest. So here you can see that L band will have the high penetration capability, so it can penetrate the canopy cover, and it can interact with the different branches and the other structure of the forest area, so that here you can see that very high return is received by the sensor in the case of L band. In the case of C band, here you can see that in comparison to the L band, in C band wavelength is small, so there is less penetration capability, so there is less penetration, so less back is scattered from the branches will be received in the case of C band for the pine forest. Now when we are coming to the X band, since it is having the very less wavelength range, approximately 3 centimeter, so most of the information will be scattered from the top of the canopy itself, so very less penetration capability will be there in the X band. Now all the SAR data sets are represented by the complex numbers. Why? Because SAR data sets should have the phase information as well as the amplitude information. So when the SAR data sets will be represented in a complex number, so it will become easy to retrieve the amplitude and the phase information of the targeted objects. Now speckle is a kind of unwanted signals which are coming due to the interference of the return signal of the SAR data set. So these are the unexpected bright and dark value. Generally dark values identification will be very difficult, but unexpected bright values could be easily visualized, and if there is a requirement, the speckle filtering could be done. So basically when the SAR signals are transmitted by the sensor, so at that time when there will be similar kind of orientation or similar kind of objects, so in the return signal it might be possible that there will be interference of the signals in the return signal. So that interference may result as constructive interference and destructive interference. So constructive interference are going to appear as the bright patches, and destructive interference are going to appear as dark patches. So mainly we are having problem with the bright patches because those are appearing as noise. So generally most of the speckle filters are the low pass filters, and this speckle effect could be minimized with the help of the speckle filters. Now most of the speckle filters are the low pass filters, but adaptive filtering approaches are also there, in which they can consider the destructive interference based dark patches also. So now here you can see that this is Terrace RX data set for the Visakhapatnam area before speckle filtering. So here you can see that in water, we know that in water we will get the specular reflection, there should be complete darkness. But due to the constructive interference in the return signal, there are bright patches we are getting. These are the unwanted signal, and it becomes very difficult to do the clear interpretation because speckle is there in the entire image. And identification could be easily done in the water body. Now after speckle filtering, here you can see that there is clear visualization of the different objects in this image. Now there are different distortions in the SAR data set, like foreshortening, layover and the shadow. When the radar beam reaches the base of the tall feature tilted toward the radar, before it reaches the top, foreshortening will occur. Here you can see in the image, the slope A to B will appear compressed and the length of the slope will be represented incorrectly. Length of the slope is represented A dash B dash, that is not the correct information. Now in this figure, we can see that the mountainous steep terrain is going to show the effect of the foreshortening, so that we are not going to get the clear information of the slope. Now when we are coming to the layover, so layover occurs when the radar beam reaches the top of the tall feature B before it reaches the base A. The return signal from the top of the feature will be received before the signal from the bottom. As a result, the top of feature is displaced toward the radar from its true position on the ground and the ledge over the base of the feature B dash to A dash. So at that time, that feature will not be visible. So here you can see that feature means slope of the terrain will not be visible. At that time, what will happen? Top of the terrain is going to completely cover the base. At that time, we will not get any information of the layover. So here you can say that layover is a kind of extreme condition of the foreshortening, in which we are not going to get any information of the layover. Layover generally occurs in the near range, and if the same terrain will be there which is giving the layover in the near range, the same terrain may give the foreshortening in the far range. So in far range generally we are getting the foreshortening, in the near range we are generally getting the layover, because we are not going to get any information of the slope. Now here due to the layover effect, we are not able to get any information of the slope. So particularly when we are talking about the near range, so that in the near range we are not able to get any information of the targeted objects. Now this is the condition of the perfect shadow. Either it is the foreshortening or layover. Opposite to the object, we are going to get the shadow. Perfect shadow condition will be there when the targeted the transmitted electromagnetic wave will hit the object in such a way that there will be appearance of shadow. So at that time we are going to get the shadow opposite to the object, so that we will not have any information of the slope opposite to the slope which is facing the radar wave. So why? Because we will have the complete shadow information. Like here you can see that due to the shadow we will not have any information of the targeted object. Now the SAR data sets could be acquired in 3 different modes: steep map mode, spotlight mode and scan mode. There are different applications of these 3 modes. In steep map mode there is moderate resolution and moderate swath. In spotlight mode there will be very high spatial resolution, but their swath size or total coverage will also very small. In scan SAR mode, the SAR data set will be acquired with coarser resolution, but the swath will also be very, very large, like in 200 kilometer or 300 kilometer. Now there are different formats of the data set: raw data, SLC data, multi-look data, geocoded data and polarimetric data. So polarimetric data we have already talked: single polarized, dual polarized and the quad pole mode data set. Raw data set, these are the simply signal responses which are received by the SAR sensor for any target. So after doing the signal processing, SLC image, single look complex images are generated. So they generally raw data set, they are named as either 1.0 or level 0 product. SLC is named as the level 1 product or 1.1 product. Multi-look data set and geocoded data set, they are named as 1.4 product or 1.5 level product. So user can download the data set according to the requirement. If one is interested to work with the polarimetry and interferometry, then it is always suggested to use the complex format of the data set, that is SLC, single look complex data set. Now this is the quad pole data set for Yellapur forest area, Karnataka. So here you can see that all the objects could be clearly seen in the different polarization. These are the back scatter images in the different polarizations: HH polarization, VB polarization, HV polarization, and VH polarization. So if you will see carefully, then only you will be able to identify the difference in the different polarimetric channels. And this is the color composite image which will be generated from the polarimetric decomposition. So here you can see that the green color is representing the dominance of volumetric scattering, blue color is representing the dominance of the specular reflection or the surface scattering, and the pink color and the red color is representing the dominance of the double bounce scattering, like the scattering from the urban areas or the vertical objects. Now there are different advantages of SAR remote sensing that we have already seen, like cloud penetration capability, night vision capability, sensitivity towards the structural and the electric properties of the targeted object, and we can use the polarimetric and interferometric phases to provide the precise target information for different applications. Now there are several advantages of SAR remote sensing. There are several applications. Generally I covers those applications in overview of SAR remote sensing. So those lectures are available on our EduSet channel. So you can simply search the overview of SAR remote sensing. There you can get the different applications, like how to get those information from the SAR data sets, what are those products finally which were generated from the SAR data set, like for DM generation, for subsidence mapping and monitoring, cryospheric glaciological applications, soil moisture content, structural and biophysical parameters retrieval, crop mapping and monitoring, flood control, oil spill monitoring. Different things could be done, volcanic structure or volcanic lava flow detection. So you can do different studies with the help of the SAR remote sensing. Now thank you for attending this lecture.